Afternoon or good morning, everyone. As said, I'm Liam Nicholson and I'm a Principal Flood Modeller at Mont MacDonald. And here today to talk about the hydraulic modelling for the LFAS2 scheme. So the first obvious element is, what is the LFAS2 scheme or Leeds Flood Alleviation Scheme? Well, it's a now completed flood risk scheme through the River Aire corridor in the west of Leeds, between Armley Bridge in the north of Bradford, through to Leeds city centre upstream of the train station, the main Leeds Central station. And why is there a need for this flood scheme? Well, really, the scheme, Leeds has had a long history of flooding, dating back to Victorian times and even before that. But it was the events of Boxing Day in 2015, Storm Ava, which really focused the need for a flood alleviation scheme for Leeds. And it was this event which caused significant damage through a lot of the communities, especially in the west, such as Kirkstall and Rodley. And like I said, some people saw the lighter side of it, but there was huge amounts of damage, estimated 37 million in damages, over 2,000 homes flooded and businesses all affected by this. So really this event focused the need for a flood alleviation scheme and that protection that Leeds desperately needed. So the scheme itself consists of a combination of linear defences through that River Aire corridor, and these provide a 1% standard of protection with the allowance for climate change. And these linear defences work in conjunction with the upstream flood storage area at Carveley, and this provides that increased level of protection of 0.5% plus climate change, a really high standard of protection which is needed for such a big metropolitan area like Leeds. And in 2019, Mont MacDonald with BAM, BMM JV, were asked to help with the detailed design, the consenting and the construction of this scheme. Now, within the River Aire corridor itself, there are numerous key and quite sensitive receptors, both communities itself, but also quite historic features, I suppose, which is the Armley Mills being one of them, which is now the Leeds Industrial Museum. And the mills itself is subject to very, very enhanced and strict heritage protection. The mill is nationally important and has internationally significant features and is also deemed to be of special interest. Now, as I say, Armley Mills is located within that corridor and, like Leeds itself, has a long history of flooding. And again, in 2015, Boxing Day 2015, the mill was significantly damaged by this flooding. Its position and its need to work with the river for historically important industrial processes leaves it exposed to this flooding when it occurs. Now, if we look at where its position is, so there is just an overview, a map of the mill complex itself, sandwiched between the Leeds and Liverpool Canal to the south, the River Aire flowing around it to the north. And what the mill complex has is this structure or control structures at the top and on the side of this, and what is referred to locally as a goit, which is just effectively an artificial channel which flows through the mill complex itself. And this goit allows water to be taken from the river, pass through the mill, and historically would be used to drive machinery and used in other industrial processes. As I say, because of its location, it's subject to that flooding, which we see in 2015 and historically before that. So what the LFAS2 scheme decided or aimed to do was to protect that. And how this complex would be protected was through walls, which are located around the outside of the mill complex, tying into that high ground to the south. But what it also required was control structures to still allow the feature of the goit to be working and usable during normal conditions. And so what the scheme consisted of at outline design were control structures at the upstream and downstream extent, and again on the side, and then the walls surrounding it. And this was what was raised, and this was the plan as we went into the detailed design. However, when we raised this and when this was looked at by the various statutory inputs and bodies, including the Environment Agency, one question was raised, or well, numerous questions were raised, but specific to this was, in order to obtain consent, they needed assurance that the goit structures that were planned were appropriately designed, not only for flood risk, but for the broader environment. And so to enable the consenting of the scheme, we had to address this query that was raised. And so what we decided in the first instance is we would hopefully and help trying to define, well, what are these broader environmental aspects? Flood risk, to many of us, is pretty self-explanatory, but what do we mean by this broader environment? Now, key to Armley Mills itself is, of course, the flood protection and how the structures operate, but there were also geomorphological, heritage, and freshwater ecology needs, which had to be identified and understood and managed. Now, for myself, as a hydraulic modeler, I could already identify where I was quite familiar, where I was comfortable, and perhaps where some of this uncharted territory was. And we were confident that we could use hydraulic modeling to help answer and help aid evidence for all of these various, both broader environment and flood protection and structure operation, but it was what that would look like and how we would go about that. And again, if we step back and just think about, well, what is hydraulic modeling? Why do we do it? Well, hydraulic modeling itself is there to help us build an evidence base, and it helps us to make more informed and confident decisions in that. So we can be pretty confident that hydraulic modeling would be good for us to use. But again, how are we going to use that? Hydraulic modeling can mean lots of different things, and there's lots of different methods that we can use to help with this. Now, one of the key aspects that we had to think about was the time frame. So we were currently in a detailed design and a construction phase of work. So there was the deadlines that we had to try and work to. There was obviously the costs element of that, so the scheme cost itself. But we also had to still have that quality and confidence in our outputs and what we would do. So our hydraulic modeling and our hydraulic modeling tool needs to balance all of these various elements of it. We need to have reliable metrics for a wide range of aspects to help with that broader environment. It also needed to be very flexible and quick in terms of working on that and quickly providing feedback to contractor and various statutory bodies. So as the modeler, I stepped into my tool shed and I looked at various options that helped balance all of these aspects and thought, well, we need the right tool for the right job. Do we need a 1D, 2D model, for example? Is that too high in cost and program? Can we do hand calcs? But does that give us the correct level of confidence in our estimates? We also need to think about what's there itself. And these are various historic structures and quite complicated structures that are located within and close to the mill complex. That being the upstream weir on the River Aire, various mill building culverts which flow below the main building, and as I said, these control structures. We need to have confidence in how these operate during both regular drought and high flow conditions. So we had a bit more of a thought and then decided that a 1D model would be the appropriate tool for us to use. And why did we select that 1D model? Well, The 1D model could give us flexibility in the simulations that we decided that we would run. It gives us the detail that we need for those key structures. Importantly, it fits the resources that we have available, both in terms of our cost and our time frame, and it's proportional to the task at hand. Now, we were confident at this stage that a 1D modelling approach would be appropriate to help us answer the question. But one of the big uncertainties we had was, well, what flows? What about our boundary conditions? Now, at this stage, we have a gauge at the bottom of the reach, which has over 50 years of data, and we could utilize that gauge data to help us provide confidence in those inflow estimates that we used. So overall, we believe and we are comfortable that we had the correct tool that was appropriate for the task at hand. So we went ahead and we started with our modeling assessments. And quickly, what we identified was the importance of one of the key structures at the upstream end of the Goit, and that was the historic sluice gate, which was, in essence, was very difficult to try and understand simply because of the uncertainty and how it operated. Now, this was regularly operated by museum staff, and during our assessment, we couldn't really pin down exactly what the operation was of this. Often it was done by judgment rather than through a set of rules. So we had to understand how sensitive this was to change and how it influenced our downstream conditions within our Goit. So what we were able to do is we were able to look at the structure itself, and because of this 1D approach, we were able to quickly test numerous sensitivities, opening position, how many gates were open, and we could quickly look at that and establish what we believed was a baseline condition. And we did that relatively quickly. Now, were we to use perhaps a different, more intense model, such as a 1D, 2D model, perhaps we wouldn't have came to this conclusion quite as quick. So already that 1D modeling approach has really given us benefits straight away. So what we were able to do was establish our baseline results. We were able to replicate observed conditions, and we were able to understand the influence of this upstream structure. So we were happy with this. We demonstrated this to the various parties, and we proceeded with subsequently looking at the impact of the scheme. Now, as it's a flood risk scheme, it was important for us to understand the flood risk. But with the flood risk, one of the key aspects we needed to understand was how the structure operated. So what we wanted to understand was how balanced the operation was. We didn't want it to operate too frequently, but also we didn't want it to operate too infrequently. So the solution that we had on this was to effectively automate the sluice gate at the top and come up with a set of control rules for us to understand and then help us with the operation of it during times of flooding. And we selected this based on thresholds of flooding within the mill complex itself. Again, really important that this was a 1D model for us because we were able to quickly test multiple solutions quite quickly and come to an answer. And with that, the outcomes were that we could get really a good level of stop the flooding, or at least alleviate that flooding through the mill complex itself. And what this figure shows is the baseline conditions and with the scheme itself. Now, as you can see, we were able to keep that level at that flooding level, our threshold that we'd identified, and pull that to below the baseline conditions. Now, this was obviously a good start. We're confident that we're alleviating and helping mitigate this flood risk. But one of the benefits we got out of this was this additional freeboard, or this additional availability of storage. And what we were able to do was identify and use this storage for surface water. So already we've been able to get our scheme to work not only to help with the fluvial flooding from the River Aire, but also provide benefits through that surface water flooding. So this is already a big win for us in terms of our ultimate aspirations for the scheme. So as we went through, we were pretty confident and we were satisfied that we'd been able to establish the flood protection requirements and the structure operation. And now it came on to those other broader environmental aspects that we were looking at. So if we first look at the geomorphological and the heritage, the mill building itself is, as I said, quite important historically. And one of the desires, or to aid with the scheme, was to help allow for the restoration of some of these heritage features. In this case, a historic water wheel feature that was used in industrial processes in the past, but also look to improve the geomorphological conditions. So what we'd established and what we'd done through our work is that we needed to allow for enough water during regular and low flows to pass through the goit to help potentially mobilize sediment and improve geomorphological conditions, but also allow for enough water to pass through the mill structure in order to be sufficient enough to turn the historic water wheel feature and help essentially with the museum a wider desire for demonstration days. So we need to balance both of these aspects. And what we'd identified was that for a day-to-day condition, we needed approximately 1.5 QMEX to pass through that upstream structure. But for demonstration days, we needed double that, approximately 3 QMEX. Now, the challenge that we have is allowing too much flow through could potentially result in a higher output of sediment than really would be appropriate for environmental needs. But we needed to somehow control that through demonstrations. So again, we can use the model to test how we wanted to look at this and develop this scheme further. And what we decided was that, well, we can have the flexibility of both an automated sluice gate that is sized to pass that regular flow of 1.5 QMEX, but also have a manually operated sluice gate, which is sized to allow that additional water through for demonstration days. And we could use the model to test this. And these images here just show basically the model and what it looked like in real life. And it's often sometimes we can get a bit, as modelers, we may focus on the modeling aspect of it, but and not quite see how it manifests itself in the real world. So this was the solution we proposed, and we used the model and we tested that. And we found that during our demonstration days, we could pass that sufficient flow through our mill building to allow that water wheel to turn, both in demonstration days. And we could also provide some additional flow to pass through the mill building to the downstream and help with some of those geomorphological issues. So again, we've been able to essentially use modeling to optimize our solution for regular and for flood flows and demonstrate how it will operate in the real world and provide those benefits not only for flood risk, but heritage and geomorphological. So if we just come back to these, we're now pretty confident that we've established these 4 categories. Now, the final one we come on to was the freshwater ecology. And to date, or during that time, we are confident that we'd established a suitable means of operation for our scheme. However, what we then identified was that freshwater ecology, there was a potential impact. So by allowing more flow through the goit, we could be impacting fish passage, and this would be unsuitable. And this was a big risk because this meant that we could potentially lead to a non-consenting of the scheme and delay and additional costs. And this was a big challenge that we had to overcome. So looking at the fish passage, this is an overview of the mill building as we see it. Normal fish passage routes were that going downstream, fish would pass through the upstream structure and out of the side structure to migrate downstream. But upstream, they would stay on the main River Aire channel. Now, by adding in our new scheme, we effectively impact those normal fish passage routes. And what that meant was that we then had the potential of allowing or promoting fish to pass through our mill building and be attracted to flows at the downstream. There was this element that we had to look at, which was called attractant flows that were raised to us by our ecologists and the Environment Agency. And that was that higher velocities would create these attractant flows, which fish would be attracted to and therefore impact their migration or their natural migration. So again, we had to look at this and understand and decide how we can help provide the evidence to demonstrate that if there was an impact, how we would manage that, and if there wasn't an impact, demonstrate the evidence to show that. So looking at this, the images of the upstream or the main kind of routes through here, at the downstream confluence, by adding in that control structure, there was a potential that those attractant flows, as I say, would attract fish towards that structure instead of where we wanted them to go, which was up the River Aire, and they would become trapped there. And at the upstream, there was again, we didn't want fish to be passing through those mill building culverts that go underneath. We wanted them to still pass out of that side and maintain what it was at the time already. Now, what we could do is we could look at the hydraulic model, and in particular, look at the velocity and look at that impact of attractant flows and identify where the fish would go. And what we were able to demonstrate is that we had those higher velocities within the River Aire. So we could use modeling evidence to demonstrate that, but we could also demonstrate that the fish would actually be attracted to that side sluice. And we were able to size our side sluice through our scheme to provide that even bigger attractant flow for the fish to pass through. So again, we've used modeling evidence to help demonstrate and answer the questions that were raised to us and demonstrate that our scheme was suitable and wouldn't have that impact on the broader environment. And so with that, we come back to this and we look at that and we say, well, we've been able to help identify and address all of these concerns that were raised to us and help us go forward in the consenting and the construction of the scheme. And it's important for us to, as modelers, to understand all of this is underpinned by hydraulic modelling. It's not just for flooding, it's for a range of other issues. We can use hydraulic modelling to provide us that evidence that we need. And so with that, we were able now to have the construction of our scheme. So as we see there in the top left, there's our upstream control structure with our two sluice gates, our automated and our manual. We were able to size the downstream control structure appropriately. We're able to put that new side sluice in there to promote that fish passage. And obviously able to help with the sizing of the flood walls and leading to other heritage benefits, such as the refurbishment of an important engine shed that was located within the mill building complex. So all of that work is underpinned by hydraulic modelling. And we were able to successfully get the scheme consented. It's now been built and currently is operational as of, I believe, just before Christmas. And with that, thank you for listening.